Welcome to the deep dive. Today we're digging into something fundamental in trigonometry, the law of cosines.
That's right.
You probably know the formula, C off A plus beat my coso.
Mm-hmm. The classic form.
It feels like, the ultimate triangle solver.
It really is. More than just the formula, it's a seriously powerful tool. It actually generalizes the Pythagorean theorem.
Which everyone knows. Yeah.
Exactly.
Oh.
And it lets you figure out triangle sides and angles when, say all three sides or maybe two sides and the angle tucked right between them.
Okay, let's pause there. Generalizes Pythagoras. How exactly? Because honestly, that connection isn't immediately obvious, is it?
Well, look at the formula again.
Yes.
C po bo equals A pol plus po equal P E. O col A-A-A-R to A poso.
Right.
Now, think about a right-angled triangle. What's the angle, Bo?
90 degrees.
And the cosine of 90 degrees is?
Zero.
Zero. So that whole last
Yes.
part, the A per B poso, it just vanishes.
And you're left with C oppose plus B up.
Exactly. So the law of cosines isn't some totally separate thing. It's like Pythagoras plus. It works for all triangles, not just the right-angled ones.
Wow. Okay, that clicks. That's actually quite elegant. So it's the more versatile tool in the kit.
Yeah.
How do we use it then practically to solve triangles?
Good question. So say you've measured two sides, A and B, and you know the angle between them.
Okay.
You can find the third side, C, just by plugging into CL plus B2 diff.
Right.
Imagine you need to know the distance across a small lake. You can measure two distances along the shore, A and B, and the angle where they meet.
Mm-hmm.
Plug them in, and bam, you've got the distance C across the water. No swimming required.
Huh. Very neat. And what if it's the other way around, if you know the sides?
Yep. If you happen to know all three sides, A, B, and C, you can find any angle. So for angle go, you rearrange the formula to arc plus O plus C.
Okay, that makes sense. You just need the sides. But what if you know two sides, but the angle you know isn't the one between them? That sounds trickier.
It can be trickier, yes. If you know, say, sides A and B and angle opposite side A.
Right, side angle. The ambiguous case.
Precisely. Applying the law of cosines here, when you try to solve for the third side C, it actually leads you to a quadratic equation.
A quadratic, why is that?
Because with that side angle information, sometimes you can't form a triangle at all. Sometimes you can form exactly one. And sometimes
You could draw two different triangles.
Exactly. Two possible triangles fit the data. The quadratic equation reflects that it can have 0, 1, or 2 real positive solutions for the length of the third side.
So the formula itself kind of anticipates that ambiguity. That's clever.
It is. And just a small side note for the computation folks, sometimes if you have a very, very skinny triangle, like with very acute angles, the way computers do the math can lead to tiny, tiny precision errors, something called round-off error.
Ah, okay. A practical consideration for engineers and programmers, maybe.
Definitely. Something to be aware of in high-precision work.
So this feels like quite a sophisticated piece of mathematics. Is it, relatively modern?
You'd think so, maybe, but actually the core idea is incredibly old. Like ancient Greece old.
No way!
Yes, Euclid. In his Elements, which is, around 300 BC,
Wow.
he laid out geometric theorems, propositions 12 and 13 in Book 2 that are essentially the law of cosines. He didn't use algebra, of course.
Right, no A's and B's and cosines.
No. He talked about it in terms of the areas of squares and rectangles built on the triangle sides. He handled obtuse triangles and acute triangles separately.
How did that work with areas?
Well, for an obtuse triangle, for instance, his proposition 12 basically says the square on the side opposite the obtuse angle is greater than the sum of the squares on the other two sides.
Okay, that sounds a bit like Pythagoras, but with an adjustment.
Exactly. It's greater by twice a specific rectangle's area. And that rectangle's area corresponds precisely to our 2 op cos git term, just expressed geometrically.
So the relationship was understood,
Yeah.
even without the symbols.
That's the key takeaway. The underlying geometric truth was there. It shows how enduring these mathematical ideas are.
Incredible, thousands of years ago.
Yeah.
So when did it start looking like the formula we use today?
Well, that took quite a while. It evolved over centuries. In the Islamic Golden Age, scholars like al-Khwarizmi and al-Battani around the 9th century used related concepts, especially in astronomy, for spherical trigonometry.
Ah, for calculations on a sphere.
Yes. But the big steps in plane trigonometry came later, particularly from Persian mathematicians. Nasr al-Din al-Lusi in the 13th century really systematized solving triangles.
Okay.
And then Jamshid al-Kashi in the 15th century, he provided a much more explicit statement. It looked a bit different from our modern form, algebraically, but it was equivalent.
How different?
Let's see. His version, if you translate it to modern notation for an obtuse gamma, might look something like C equals the square root of b plus a times the absolute value of cos coso, all squared, plus a sin quo squared.
Okay. Definitely looks different.
It does, but you can manipulate it algebraically and get right back to sin cos apples is sim post post 2 post so. It was a huge step. In fact, in France, sometimes they still call it the Théorème d'Al-Kashi.
In his honor. Nice.
Yeah. Then later, people like Regiomontanus in the 15th century and François Viet in the 16th century were key in bringing this knowledge to Europe and developing the symbolic algebra we rely on.
Viet, right, the father of modern algebra, kind of.
You could say that. It wasn't really until the early 19th century, though, that the formula settled into the clean symbolic form we recognize instantly today.
What a journey for one formula. Now, something this fundamental.
Yeah.
I bet there isn't just one way to prove it works, right?
Oh, absolutely not. That's one of the beautiful things about mathematics, isn't it? Seeing how different paths lead to the same truth. The law of cosines has numerous proofs.
Like what?
Well, you can actually derive it using the Pythagorean theorem itself. You drop an altitude, create some right triangles, and work through the algebra. You often have to consider acute and obtuse cases separately, like Euclid did initially.
Okay, building on the foundation.
Exactly. Or you could use coordinate geometry. Plop the triangle onto a Cartesian plane, assign coordinates to the vertices, and use the distance formula. That often gives a nice, clean proof that covers all cases at once.
The power of coordinates.
Definitely. Then there are purely geometric proofs, some quite visual, involving dissecting shapes and rearranging them, sort of cut and paste proofs.
Like proving Pythagoras with squares.
Similar idea, yes. You can also use theorems from circle geometry, like Ptolemy's theorem about cyclic quadrilaterals, or things like the power of a point theorem.
Wow, connections everywhere.
Right. You can even prove it using the law of sines and some trigonometric identities, showing how these rules are interconnected.
So they're part of a bigger system.
Precisely. And another elegant way is using vectors.
Vectors.
You represent the sides as vectors, then the relationship falls out quite naturally from the properties of the dot product. It's very concise.
So each proof kind of illuminates the law from a different angle, mathematically speaking.
That's a perfect way to put it. It shows the richness and interconnectedness of mathematical ideas. We don't have time to go through each one now, but just knowing they exist is, I think, quite inspiring.
Definitely. It's not just some arbitrary rule someone made up.
Yeah.
Okay, what about special cases or maybe extensions of this law?
Yes, there are some interesting ones. For instance, if you have an isosceles triangle where two sides are equal, say A, B,
Okay.
the law of cosines simplifies quite nicely. You get something like cos 1a point 2a, or rearranging C2a times 1 area. Well, it's a bit cleaner.
Useful if you know you have that symmetry.
Exactly. And then going further afield, there's actually an analog of the law of cosines for tetrahedra.
Tetrahedra, you mean like 3D triangles, pyramids.
A pyramid with a triangular base. Yes, a tetrahedron. This version relates the areas of the four faces to the dihedral angles between them.
Dihedral angles.
The angles between the faces. Imagine closing a book partway. The angle between the covers is a dihedral angle.
Wow. So it scales up to 3D. That's mind-blowing.
It is quite something. It shows how fundamental geometric relationships can persist in higher dimensions.
Any other variations?
Well, there's a version that's particularly useful for computations when the angle is very small. It uses the half angle or Haversine.
Haversine.
Yeah, it looks like c equal y plus 4 absine.
Right.
This form is numerically more stable, less prone to those round-off errors we mentioned earlier, especially if sides A and B are very close in length too.
So it's a practical tweak for calculations.
Precisely. And maybe the most fascinating extension is to non-Euclidean geometries.
Okay, now you're really stretching my brain. Like geometry on a sphere or...
Yeah. Exactly. Spherical geometry, like the surface of the Earth, or hyperbolic geometry, which is kind of saddle-shaped. In these geometries, the familiar rules change.
I see.
The law of cosines still exists, but the formulas are different. On a sphere, for instance, there's a law relating the sides, which are arcs of great circles, and the angles, and another one relating the angles and the sides.
Wait, angles determine sides.
In spherical and hyperbolic geometry, yes. Unlike in our flat Euclidean world, where similar triangles can be different sizes, in these curved spaces, the angles of a triangle do constrain its side lengths. It's a fundamental difference.
That really changes things. So there's a spherical law of cosines and a hyperbolic one.
Yes, several versions for each, actually, connecting sides and angles in their own unique ways. It opens up whole new worlds of geometry.
This has been, well, genuinely enlightening. The law of cosines is so much more than I remembered from school. It's not just a formula.
Not at all.
It's this deep principle connecting geometry, algebra, history, even these exotic non-Euclidean spaces.
It really is a cornerstone concept, foundational for trigonometry, obviously, but its echoes are felt in physics, engineering, surveying, navigation. So many areas rely on accurately relating sides and angles.
Absolutely. It's a testament to the power and beauty of mathematics.
Couldn't agree more.
So for you, the learner, listening right now, think about that. This fundamental rule, C, A plus BTAE, 2 apple of sec, connecting sides and angles. How does it quietly underpin so much of the calculated world around us, from building bridges to guiding satellites? And what other seemingly simple mathematical ideas might hold that kind of hidden depth and far-reaching power?
A great thought to ponder.
Indeed. Thank you for joining us on this deep dive. We hope you'll continue exploring the amazing structures and connections within mathematics.